Dear colleagues, dear academic community members of the Babeş-Bolyai University, welcome to a new presentation from the series of conferences organized within the Studium Generale program of the STAR-UBB Institute, the interdisciplinary meeting place of teachers, researchers and students of Babeş-Bolyai University. This week we move to a very large scale. Cosmology, defined as the study of the universe considered as a single object, has seen an extraordinary development in recent decades. Today's presentation is an introduction to this fascinating topic, and the title of the presentation is From the Big Bang to the Accelerating Universe, a brief introduction to cosmology. Our guest today is Harkó Tibor. He is a researcher of the STAR-UBB Institute. He was a bachelor student at the Faculty of Physics, Babeş-Bolyai University. Then he was a high school teacher, then a research scientist at different research institutes in Cluj. Later, he obtained his PhD degree at the University of Hong Kong in the field of theoretical astrophysics. He was then a postdoctoral fellow and research assistant professor and honorary associate professor at the same university. He was also an honorary and senior honorary research associate at the University of College London and then professor at the Sun Yat-sen University in China. He spent more than 20 years in China, and in the past few years he returned to Cluj, being now a researcher at the STAR Institute of Babeş-Bolyai University, and he is helping us at the Faculty of Physics by teaching astrophysics and cosmology. According to the scientometric indicators, Tibor is a highly cited researcher. He is very active in the field of astrophysics, and he is participating in many international research collaborations. Before inviting Tibor Harkó to introduce us to this very interesting topic, I would like to remind the audience, the online audience, that they can ask questions live at the Babeş-Bolyai University's YouTube channel, where the conference is broadcast. At the end, I will take the questions from the chat, and I will address them to our guest. Dr. Harkó, thank you very much for accepting our invitation to be here at the Taylor's Bastion of Cluj, and we look forward to your presentation.
Thank you very much for this very nice introduction. I would also like to say all of you, I am very glad to be here and to give a talk on this subject, which I find very fascinating and to which I did devote most of my career, scientific career. And the title of my talk is From the Big Bang to the Accelerating Universe. But in fact, my goal is to provide you with a very brief and I hope clear introduction to an important science, an important branch of present-day physics, which is called cosmology. So in my talk, I will first of all remind you what is cosmology. Then we will briefly discuss the observational basis of cosmology. And unfortunately, to understand cosmology and generally gravitational physics, we need a good knowledge of an important field of physics, which is called general relativity. So I will very briefly mention a few ideas about general relativity. I will present to you then relativistic cosmology, what it is present status. I will go to one of my important topics of my talk, which is the accelerating universe. And probably I will end with the most interesting question, which what the future will bring to us, that is what kind of future developments may take place in cosmology and how will they affect our knowledge. So first of all, very briefly, I define cosmology, which is the study of the universe, of its components, how it formed, how it has evolved, and what its future is. More exactly, cosmology sees the entire universe as a single atom. In this way, it is somehow analogous to the atomic physics, where also we have a fundamental object, a fundamental particle, which is the atom. And of course, we study the components of the atom, the electrons, and so on, various interactions. But I would like to point out a very important difference between, let's say, atomic physics and cosmology. While in atomic physics the atom is unchanged, the universe is changing. And this is one of the most important and one of the most interesting aspects in cosmology. We are living in a universe which is very rapidly changing, which is today in a form, but yesterday it was in another form, and perhaps tomorrow will be in a fully different form. Cosmology is essentially an observational science, and its history goes back to around 120 years ago, the history of modern cosmology. And basically, the cosmology was born from technical progress in the field of astronomy, observation and observational astrophysics, and this was related to the possibility of measuring the Doppler shifts of the spectral lines. Now, it is hopefully a well-known physical effect, that is the wavelengths of radiation changes depending on the motion of the emitter. If the object is moving away from us, the spectral lines are displaced towards the blue part of the spectrum. But if the objects, the emitting objects, are coming closer to us, the light is displaced towards the red part of the spectrum. And these measurements were initiated around 100 years ago by the American astronomer Vestos Leifer. And he studied around 40 galaxies by 1925. And what was the standard expectation of the astronomers? That probably half of the galaxies will have blue shifted spectral lines, and the other half may be red shifted spectral lines. That is, the motion of the galaxy should be more or less stochastic in a non-evolving universe. However, what Leifer did observe is that in fact all galaxies have red-shifted spectra. This means that all the galaxies were moving away from us, were receding from the Earth. And not only the galaxies are moving away from the Earth, but they are also moving away from each others. So this was the first important observational aspect of cosmology. Another very important development came also around 100 years ago, and it is related to mostly to the work of Edwin Hubble, who is probably the most distinguished astronomer of the past 100 years. And he made a significant progress in the field of astronomy and astrophysics by providing a very precise method of the determination of the distances to celestial objects. This is still an important and, I may say, open problem in astronomy, how to determine distances to galaxies, stars, and so on. There are many methods, but essentially Hubble used a method based on some stars, which are called the Cepheid stars. And what is interesting from these stars is that they are pulsating stars. Their luminosity changes in a periodic way. Now there is a relation between the luminosity and the period. And once we determine the period, we can obtain the luminosity of the star at the source, we can measure the luminosity on Earth, and from this we can infer the distance to the stars or to the galaxies. Now, Hubble also studied the same galaxies, the same systems as Slipher. And he was also able to accurately determine the distances to those galaxies. And at this moment, I may say, one of the most important events in physics occurred, even it looks very simple, because Hubble combined his results on the measurement of the distance with Slipher's measurements of the velocities. And what did he find is this very simple, but in fact amazing plot. Because it shows that there is a linear relationship between the recessional velocity, the velocity of expansion of the galaxies, and their distance. This figure is very simple, and it leads to also a very simple relation between velocity and distance, that is v is equal to a constant multiplied by the distance. This is called today's Hubble's law, and this constant H is a very important constant in physics, which is called the Hubble constant. Now, this simple figure has in fact some amazing implications. First of all, it means that the universe is not a static system as it was believed before Hubble, but it is a system which has an intrinsic and large-scale dynamics. This is the first implication of Hubble's law. And in fact, everything in the universe is expanding. This is valid for galaxies, for stars, even for atoms, but in this case, the effects are very, very small. So, the universe is expanding, the universe is growing up, but this has another equally important implication. Because let's reverse the direction of the expansion, and this means that in the past, the galaxies and the matter were much closer to each other as they are today. And in fact, if we go further and further by applying Hubble's law, we arrive to the conclusion that all the galaxies and all the space and all the matter simultaneously converge to a single point. And in fact, the universe was born in very specific initial conditions. And this led to an absolutely fantastic change in the cosmological paradigms ever proposed in cosmology, because it led to the conclusion that in fact the universe originated from a single, let's call it point, but more precise, it would be a very small volume, but let's not go into these technical details. And this model, in which the universe originated from a singular point in a very special physical state and having a very, very small dimensions, is today known as the Big Bang theory. Some of you may be familiar with the Big Bang theory from the series with the same name, which maybe some of you did watch on TV. But anyway, this was a very drastic change in our understanding of how the world works. But the Big Bang theory must be credited to another very important figure in science, relatively little known, the Belgian astrophysicist Georges Lemaitre. And he was the first to propose the idea that galaxies originated as fragments ejected by the explosion of some kind primordial or original atom. Now, the Big Bang theory was not accepted for a relatively long time by the scientific community. And generally, it was mostly ridiculed in its early stages. And Einstein was a critic of the Big Bang theory, and another important scientist who also adopted a very critical view was the British astrophysicist Fred Hoyle, who said that it is impossible that the universe was suddenly born with a big noise. And this is the name Big Bang from the name Big Bang, in fact, means the big noise Fred Hoyle attributed to the birth of the universe. So I may say for around 40 years in the development of physics from the 1920s to the late 1960s, the Big Bang theory was seen as a marginal theory in physics, despite its having a very firm observational basis in the expansion of the universe and in Hubble's law. But this changed dramatically and drastically, I may say, with the discovery of the microwave background radiation. Because if the universe was suddenly born, it should have been in the form of light, in the form of electromagnetic radiation. And it was very, very hot, but due to its expansion, the universe cooled down. And the radiation from the very early times must also be present in the present-day universe. The expansion of the universe led to the cooling down of the radiation, but its remnants are still here, and they are a very powerful evidence for the Big Bang. Now, this discovery was made, in fact, by two engineers working in the Bell laboratories in the United States, Penzias and Wilson, who, in fact, were looking for something else. And they built an antenna on a specific wavelength, and it turns out that on that wavelength there is a noise. It was a noise. And the engineers tried their best to eliminate this noise. They looked for any causes and any technical problems, but without success. However, this is another fortunate event in the history of physics. Penzias and Wilson went to the Princeton University, where they met a physicist called Dickey, and they told him about this problem. But it was the physicist Dickey who realized that what Penzias and Wilson did detect was the microwave background radiation, that is a remnant from the Big Bang. And presently, the most powerful evidence for the Big Bang, together with Hubble's law, is the cosmic microwave background radiation. Because the initially very hot radiation cooled down at a temperature of 2.7 degrees Kelvin, but it is a very, very strong and powerful evidence for the Big Bang. It is difficult to believe that, in fact, in this room, probably there are photons who originated from the Big Bang. And some not very complicated antennas, in fact, could detect these photons, let's say, even in our town. So basically, the universe is filled with an electromagnetic radiation that presently has 2.7 kelvins and which originated from the Big Bang. Now, the topics of the cosmic microwave background is a very big one. And I will not go into these details. What is interesting is that the spectrum of this radiation is a perfect black body. And it is such a perfect black body that it is better than the one that could be created even in the laboratory. There are a number of important physical consequences that can be obtained from the cosmic microwave background radiation. And the first important information is related to its distribution. So this radiation is largely isotropic, and this is a very strong evidence that the universe itself is also isotropic. However, in the microwave background radiation, there are very, very small anisotropies, but these are of the order of 10 to the power minus 5 kelvins. 10 to the power minus 5 kelvins. And these anisotropies can also give us very important information on the galaxy formation and the evolution of the universe. And they are a very important field of study, and they have been studied especially by satellite experiments. There are 3 famous satellite experiments devoted to the detection and study of the CMB. The first was COBE, and George Smoot, who was the chief scientist, was awarded the Nobel Prize for this experiment. Then it was the WMAP experiment, which led to an improvement on the quality of the data, as you can observe in these pictures of a child. And presently we also have the Planck experiment, the Planck satellite. The data have been released relatively recently, and which also led to an improvement of the study of the CMB. This is still a very active field of research and fundamental, and a lot of information about the universe can be learned from these experiments. So the CMB is on one hand very isotropic, and secondly the small anisotropies can give us important information about the fluctuations of the density and galaxy formation. But this is related to the observational basis of cosmology, which there are many, but essentially in a very simplistic view, can be reduced to the idea of the expansion of the universe observed by Hubble and to the CMB. These are the observational foundations of cosmology. But what about the theoretical issues? Can we understand these observational facts in the framework of some theory? And the answer is yes, and the theory that gives us a very good description of cosmology is called general relativity. Now, general relativity is a very big and very important field of science, which I will not go into too many details. General theory of relativity originated from special theory of relativity, which is based on one of the fundamental experiments in physics, the Michelson and Morley experiment, which did find out that the speed of light is an absolute constant. It doesn't depend on the motion of the observer. The Michelson and Morley experiment was used by Albert Einstein together with the principle of relativity to propose the special theory of relativity, which is based on 2 very simple postulates: that the laws of nature are the same in all inertial frames of reference, and that the speed of light in the vacuum is the same in all inertial frames. This is the Michelson and Morley experiment. Now, these 2 very simple postulates led to a number of amazing physical effects. I very briefly, I mentioned here the time dilation, the length contraction, the relativity of space and time and their dependence of the observer, and also the fact that we cannot think of space and time as separate entities. Probably one of the most important early implications of special relativity was the unification of space and time in a single four-dimensional geometric structure. But this idea of the four-dimensional space-time belongs to the mathematician Hermann Minkowski, who, by the way, was a teacher of Einstein. Anyway, relativity led to the conclusion that space and time are fused together to form a four-dimensional space-time continuum. But even the consequences of special relativity are already amazing. Einstein developed this theory into what is called today the general theory of relativity. In this he was helped very much by one of his friends, Marcel Grossmann, who was a professor of geometry in Zurich. So the general theory of relativity is essentially a theory of the gravitational field. It is an absolutely amazing theory of the gravitational field, and it is based on Einstein's lift experiments. Einstein used the lift, but we may use also some space rockets for similar experiments. And essentially, these lift experiments are very easy to be understood. Because let's say we are in a rocket that is accelerated upwards by an acceleration g, being the acceleration of the gravitational field on Earth. Inside the lift or inside the rocket, a gravitational field which is equivalent to the one on Earth is created. And if the lift or the rocket is accelerated downwards, basically with this negative acceleration we can cancel, let's see, the gravitational field of the Earth. And this type of thought experiments, as well as some other issues, led Einstein to introduce the so-called principle of equivalence, that in a simple formulation states that gravitation and acceleration are equivalent. So in the general theory of relativity, gravitation is not due to the exchange of particles, be they photons, mesons, or some other particles like in elementary particle field theory, but essentially it is an effect due to the accelerated motion of reference frames. Now, if this is the case, we have a much important implication, and namely, gravitation is also a consequence of the curvature of the space-time. There is a simple way to go from acceleration to curvature, but in general theory of relativity, gravitation is a result of the presence of the curved geometry of the space-time. So, planets, for example, they do not move on their orbits because they are somehow attracted by the sun through some exchange of particles, let's call them gravitons. They move because simply the sun, as a very massive object, curves the space-time of the solar system, and therefore planets, they just move as on the shortest trajectories in this curved geometry, in this curved space-time. And Einstein also proposed some very remarkable equations describing the gravitational effects and their relation with curvature. And these are called Einstein equations, and they are probably among the most beautiful equations ever proposed in physics. And they have a very simple formulation in words, that is, the curvature of the space-time is proportional to the matter content. And these equations can also be interpreted as meaning the curvature is equivalent to gravity. So this is the mathematical form of the Einstein field equations. And if mathematics is too complicated, maybe one can understand them in a qualitative way, in the sense that matter tells space-time how to curve, and space-time tells matter how to move. This is the essential idea of Einstein's general relativity. The general theory of relativity has a lot of observational support, the deflection of light by the sun, the perihelion precession of Mercury, the existence of black holes, and many other interesting gravitational effects have been observed, and they all have confirmed the predictions of the general theory of relativity. But Einstein also made an important contribution in 1917 when he built the first scientific cosmological model. Now, Einstein didn't know that the universe is in fact expanding, and he tried to propose a model for a static and homogeneous universe having a spherical geometry. However, it turns out that this was impossible. Einstein's equations somehow didn't want to allow such a model, and Einstein generalized his initial equations by introducing a constant, something called a cosmological constant. And this term, in fact, acts as some kind of anti-gravitational term. And once it is introduced in his equations, he could obtain a static model of the universe. However, a few years later, the Russian mathematician Alexander Friedman realized that Einstein's equations could in fact describe an expanding universe. And he obtained such a solution, and in fact his solutions, based on his famous equations, the so-called Friedman equations, imply that the universe indeed have an origin. They imply that the universe was indeed born, let's say, 10,000 million years ago in the past, and it may have been some kind of initial burst that generated the matter, which ever since travels and expands in the universe. And the theoretical model based on Friedman's equations also confirms Hubble's observations that all the matter, and in fact the universe itself, was created at just one instant. Now, technically, these are Einstein's equations and these are Friedman's equations, but I don't want to go into these technical issues. Einstein added the cosmological constant to these equations. This is the lambda term, which was added by Einstein in 1917. And interestingly enough, this lambda term is at the center of present-day developments in cosmology and largely in physics. Anyway, the cosmological constant had a very interesting history which would deserve a special analysis. because after learning by Hubble's and Friedman's work, Einstein decided to eliminate this constant from his theory and called lambda, the cosmological constant, the biggest blunder of my life, the biggest blunder of his life. Also in a letter to Lemaitre, Einstein wrote, "I am unable to believe that such an ugly thing should be realized in nature." This is very strange because today we know that the cosmological constant or something analogous exists in nature, and it is what triggers the so-called accelerated expansion of the universe. Anyway, cosmology, the traditional cosmology, has three models related to their geometry. And the geometry is in fact determined by the density of matter. There is a so-called critical value of the density. If the density is smaller than the critical density, the universe is called open. If it is higher, the universe is called closed. And if it is equal to the critical density, the universe is called flat. So these are some intuitive representations of the possible observation, of the possible geometries of the universe and of their characteristics, but observations, especially those of the cosmic microwave background, did show that the actual geometry of the universe is in flat, and it may seem that the universe has exactly the critical density. So all these universes have very interesting geometric and other physical features, but again, we do not have the time to go into these issues. But here is just a representation how, in fact, it was inferred that the geometry of the universe is flat from the study of the CMB. The fluctuations in the three geometries are very different if the universe is open, flat, or closed. So these fluctuations can be obtained theoretically, and then comparing these theoretical models with the CMB data, one can infer about the geometry of the universe. So by around 25 years ago, cosmology was a very quiet field in which there were a very well-established model. We did have Einstein's equations, we did have the CMB determinations by Kobe, and it seemed that everything was more or less known, except perhaps the mystery of the Big Bang. But by around the year 2000, a very important evolution occurred in cosmology, and this is related to the discovery of the so-called accelerating universe. This discovery was made by three groups of people, one led by Saul Perlmutter, the other one by Adam Rees, and the third by Brian Schmidt. Their goal, the goal of these teams was in fact, I may say, very modest. They wanted to improve the determination of the cosmological parameters by using the properties of the supernovae. Supernovae are very interesting cosmic events. They are the explosions of stars. Stars explode and they generate a lot of energy. Now, there are many supernovae. Some are called the classic supernovae in the sense that they have been observed a long time ago, like the one in 1054, and they have been recorded in those times, and this is very important because we know exactly the age of the supernova. Because in 1054 there were no astronomical records, let's say, in Europe, but we have a supernova whose age is very well known. Okay, what is the importance of the supernovae for cosmology? Even that they are rare events, they can still be detected by the modern telescopes. And there are many types of supernovae, but for cosmology, the most important are the supernovae type 1a. Supernovae type 1a. Why are these supernovae important? They are important because they are in fact the explosion of a very specific type of star which are called white dwarfs. Generally, the supernova explosion occurs in a binary system in which we have a white dwarf and another companion star. Now, from the white dwarf having a very massive gravitational field, accretes a lot of matter from the companion star. And at some moment, the mass of the white dwarf becomes 1.4 solar masses. 1.4 is a very important number in astronomy. It is the so-called Chandrasekhar limit, because the Indian-American astrophysicist Chandrasekhar did prove that if the mass of the white dwarf reaches this value, it will become unstable, or more exactly, it may explode. Now, this means that the explosion of a supernova type 1a occurs when the star has a very fixed mass and, of course, very fixed other astrophysical properties. And this means that we know the luminosity of the exploding supernova. We know the luminosity at the source, we can measure the luminosity on Earth, and from this information we can obtain the distance to that star. Okay, so if the mass of the white dwarfs exceeds 1.4 solar masses, it is no longer stable against collapse, and a thermonuclear explosion is generated, and basically the entire star disappears in this huge explosion. And this is important because we can, as I mentioned, we can obtain the luminosity, and this type of supernovae, they can serve as standard candles, and they can indicate distance within space. So the three teams I have mentioned wanted to use supernovae to improve our knowledge on the cosmological and astrophysical parameters by using various observations and various telescopes. However, what they did find was something extremely unexpected, because the supernovae, in fact, after calculating their distances, were not located where the standard model of cosmology of those times assumed to be. So one could determine the distance to the supernovae, and one can use the theoretical model to compute the same distance. And it turns out that, in fact, the observations and the theoretical model were very different, in the sense that the supernovae were much far away than the cosmological model of those times indicated. And this generated one of the biggest crises in the history of cosmology, and probably even in physics, the so-called problem of the accelerating universe. Why are the supernovae much farther than we expect? This is probably because at some moment the expansion of the universe did speed up. So the universe began to expand much faster around 1 billion years ago than we would expect from the standard Friedmann equations as they were proposed in 1920, and they were assumed to be correct up to the year around 2000. So there is a lot of observational evidence that in fact the supernovae, that the universe is expanding much faster than initially thought. And these results come from the study of the supernovae. So there are here many technical issues I would not like to go into. But as I mentioned, this discovery raised the very interesting and important problem about what is the source of the acceleration. What is the source of the accelerations? What makes the universe to move faster and faster than we initially thought? And presently, it is largely assumed that the component that make the universe to expand much faster is something we call today dark energy. In order for the universe to move as observed, dark energy must make 73% around of the energy composition of the universe. So the dominant component of the universe is dark energy, which pushes galaxies to move faster and faster. Not only we have this dark energy about which we do not know much, but there is another component which is called dark matter, also of unknown identity. And if we add this together, it turns out that 95% of the universe consists of two components we do not have any good knowledge about. What we know very well is the baryonic matter, atoms, protons, nuclei, electrons, etc. But they represent only 5% of the composition of the universe. So 95% consists of something which we do not have any very clear and very well tested knowledge. So the next question is, what could be the dark energy? There are countless proposals about what could trigger the accelerated expansion of the universe, but a new paradigm did occur, that in fact the dark energy and the accelerated expansion of the universe is due to the cosmological constant lambda. That term in the Einstein field equations, Einstein called a very ugly term, which is impossible to be realized in nature. So presently, there is a lot of evidence that perhaps the cosmological constant is not just a simple constant appearing in Einstein's equations, but most probably is another fundamental constant of nature, which some people add to the speed of light, the gravitational constant, the Planck constant, and most probably these three constants could be enlarged by adding also this new cosmological constant, which is possibly a new fundamental constant of nature. Anyway, once we introduce back the cosmological constant in the gravitational field equations, we obtain a very good description of the present-day observational data. However, the physics community doesn't like very much the idea of the cosmological constant, in the sense that presently we do not have any physical or geometrical understanding of it. We do not know basically what the cosmological constant is. We do not have any theoretical model that could explain the cosmological constant, and the only and a very good and popular theoretical model of the interpretation of the cosmological constant as the vacuum energy. This is an idea coming from quantum field theory and quantum mechanics, led to what is called the worst prediction in physics, because the differences between the quantum mechanical prediction and observations is of the order of 10 to the power 120. 10 to the power 120 is the difference between these two predictions, the worst prediction in theoretical physics. We do have also the problem of the dark matter, but I will not go into this issue. It is also a very mysterious phenomenon which is not fully understood. In fact, it is not understood at all. But if we go back to our cosmological models, to the three classic models, we need to add probably the more realistic model based on observations, and this is the accelerating universe in the presence of a cosmological constant or of a dark energy, a universe which is accelerating faster and faster. Very soon, the expansion of the universe will be exponential. In the standard Friedman cosmology, the expansion is power law. But if you assume dark energy or the cosmological constant, this expansion is exponential, and indeed the universe is moving faster and faster and faster towards an unknown future. What will be the future of this very rapidly expanding universe is another issue I will not go into. Anyway, there are many alternative candidates for dark energy. It is a very big field. Scientists are very passionate about this issue. Every day you have at least 5 papers proposing new models of dark energy and dark matter. And this is certainly presently the hottest field of physics, with a very intense activity and very many people very much interested in this field and willing to do some contributions for the understanding of these very interesting situations that did appear in cosmology and generally in our understanding of the large-scale structure of the universe. So my first conclusions would be related to this problem of the dark energy. The cosmological constant may indeed provide some explanations for some puzzles in modern cosmology. And of course, we can go back to Einstein's legacy and ask if this was the biggest blunder of Einstein, or perhaps it may prove to be his biggest achievement. Because indeed, if dark energy is it can be proven convincingly that it is the cosmological constant, probably this may be called one of the biggest, if not the biggest, achievements by Einstein. But we are still facing the problem that we do not know any origin of the cosmological constant. We do not know about the origin of the cosmological constant. But there is another part I would like to briefly mention, which is what the future will bring to us. But before going to this, I would like to read to you some very beautiful words written by a journalist who wrote that one of the great things about astronomy is that there is still so much out there for us to discover. There are so many unanswered questions and mysteries about the universe, and there is always a puzzle to solve, and that is part of beauty. Of beauty of astronomy, astrophysics, and related sciences. And even in our own neighborhood, there are many questions we still have not been able to answer. And probably I did convince you that the Big Bang did exist, but if we follow the most recent discoveries of the James Webb Space Telescope, a number of very intriguing questions were formulated. These observations led to some very amazing conclusions about how the early universe may have looked like. And this image, which is presently created based on these observations, are very different from what we believed, let's say, a few years ago. And there are a number of approaches, a number of observational results, in fact, that raises some questions about if the Big Bang really happened. I don't know what is the answer to these questions. I don't know if those observations are correct as they are interpreted. This would again require an entire seminar and entire presentation. But it may be possible that very big changes may occur in the very near future in cosmology, changes that would completely overthrow, hopefully not all I did tell you, but probably some essential aspects of the early universe cosmology. And that's why, in fact, cosmology, astrophysics, and related sciences are so fascinating and so interesting, because what we know today may not be correct tomorrow. Thank you very much for your kind attention. This is the end of my talk.
Thank you very much for this really, really interesting presentation. Now the talk is open for questions. First of all, if you permit, I find a question posted on the YouTube channel of where the presentation was broadcast.
Yes.
Adrian Brunzanic's question is the following. Are you familiar with Penrose's conformal cyclic cosmology? If so, what's your take on it?
Yes, a number of scientists, including beginning first of all with Fred Hoyle and more recently Roger Penrose, have tried to eliminate this idea of the origin of the universe, of the Big Bang creation in just an instant, by assuming a cyclic universe, a universe that exists forever, a universe that expands, and after expansion it is followed by a phase of contraction, and so on, so on. This matter exists forever, the universe exists forever, and in this way the Big Bang problem, which some people find somehow worrying, can be solved. This is the basic idea, to obtain a cyclic universe without beginning and without end. Now, from a technical point of view, Penrose uses another very interesting issue in physics related to the problem of the conformal invariance. It turns out that most of the laws of elementary particle physics are invariant with respect to the group of conformal transformations. But gravity is not, the gravitational field is not. But Penrose did build a theory which is conformal invariant, and in this conformal invariant theory, this idea of a universe without end and without beginning can be very nicely interpreted. I don't know if my answer is enough.
Thank you. If there are any questions from the audience who is here in the Taylor Bastion. Yes.
If I may follow up on the question from a student, actually, if I'm understanding correctly, we would be extrapolating to a point where everything would be concentrated in one point in the universe. So can we then naively pinpoint that is the center, the origin of the universe? But would it, I mean, if all the matter and the energy is concentrated there, is it not true that at that point, distance or space and time don't have any meaning, so there is, you cannot call that a point, which then sort of maybe brings me towards that Penrose line of thought.
Yes, first of all, I would like to point out that this idea of a single point is relatively misleading, and it is used just to describe a very small volume, a very small volume. So most probably the universe did not originate from what we call a mathematical point. It was a small volume. Interestingly, in this respect, the latest observation by the James Webb Telescope also point out that the early universe at the Big Bang may have had a bigger size than that mathematical point, which is mostly used in the popular presentations of the topic. So this is the first issue. It was not a point, it was a small volume, very small as compared to the present size of the universe. Secondly, the problem of the center of the universe, the problem of the existence of the center, here the answer is that at least presently the universe doesn't have any center. And this can be proven very well because all observers see the expansion of the universe in the same way according to Hubble's law. So once matter was created, the observers in that universe couldn't claim the existence of any center.